Hello everyone. Is it, can you hear me?
Yeah. Good morning.
Good morning.
Good morning.
There is that what?
Is everyone there on your side?
Toy and Sifa, is everybody on your side all there?
Cannot record, they blocked it.
Okay. So, not moving. So for this training, we will cover from introduction on a crazy solution. The iFeeder advantage includes summary of the iFeeder and also package of iFeeder and StreamTalk. And then we will go through the installation and iFeeder deployment, include SOP, equipment and component needed, checklist, troubleshooting and operation on iFeeder, role and responsibilities, and also the Q&A session. Okay, so for aquatic solution, we have a few solutions include of water quality, physical sensor and chemical sensor. The iFeeder include hydrophone and automated feeder. The iFeeder analysis that help to monitor the stream appetite and also stream stress level. We also have AI technology that help to do biomass prediction and growth anomaly detection, and also AquaEasy app that show real-time data analysis and also action notification. So I will pass to Ivan for the iFeeder advantage.
Okay, so today's session, basically we just be focusing on the iFeeder. What I'll be presenting basically will be the results for the iFeeder so far in all the major trials that we've done, both in Vietnam, Indonesia, and Singapore. The results that were collated is actually based on the original plan to compare the number of ponds that we are comparing. Okay, so I'll go through the details. I want to start first to talk about how the iFeeder works, because I'm not sure if everybody understands how the iFeeder works. Basically, this is a good example of how the whole process works. The iFeeder actually starts with the feeder dispensing feed in the water. And when the feed falls into the water, the streams will start to feed on the pellets. So there are multiple behaviors that we capture during the feeding session. For example, the feeding frenzy, the feeding sound. The feeding sound itself is well documented and well researched. There are research papers already written about this. I sent them out before. And they are basically called clicks. And these clicks have known frequencies in terms of their frequency component when they are feeding. There are known frequencies that we can capture and analyze. So this information is aggregated together with the feeding behavior, the way the streams behave and act in the water, to help us to figure out whether we should feed more or feed less. This signal, the stream sound, is captured by a specific sensor called a hydrophone. And this hydrophone is the small little round thing that we put in the pond. It is called a passive sonar. So there are two types of sonar. One is an active sonar, the other is a passive sonar. Ours is a passive sonar, means it doesn't send out any waves. It actually only receives vibration waves in the water. So this signal that the hydrophone captures is then processed by our own algorithms. And these processed signals helps us to capture different patterns and behaviors that the streams produce in the water. And these patterns are then actually evaluated by our AI to make some decisions. Okay, so at this point, actually, this AI is not complete. We are currently running a set of rules, what we call heuristics, that we have learned over the different trials. What the plan is actually that in the future, we will slowly move towards a fully AI-based system. Yeah, but in order for this AI to work, basically we still need labeled data. We need to introduce an appropriate algorithm to do the machine learning. Okay, this particular portion is still in the development. Okay, and then what happens is that this AI engine then controls the auto feeder to send out signals to either turn auto feeder on or off. And we do this by just controlling the power supply of the auto feeder. We don't integrate with the mechanics of the auto feeder. We just trigger them based on the power supply. So that's why we have to do dispense rate testing so that we know that for a fixed amount of time that we turn it on, how much feed actually are we dispensing into the water. So roughly that's how the eye feeder works. Okay, there's something else. Okay. Okay, so I'll go to the results. For the results portion, I will go fairly quickly because I think those of you who have been in the trials, you know the results already. So I will just talk in general. So the Vietnam trial that we did with Vietwook, we did 4 ponds. 2 ponds were handled by their technicians. 2 ponds were handled by the eye feeder. 11 and 12 was the eye feeder, and 13 and 14 was the technician managed ponds. The Vietwook trial actually was a bit different because it's done indoors, and also the ponds use the biofloc system. So the overall density is about the same. 1 pond at 230 pieces per square meter. The other one is 270 pieces per square meter. Okay, the other challenge with Vietwook is that in the Vietwook setup, actually they have these diffusers all over the pond. So these diffusers provide oxygen to maintain the pond during the entire culturing. And this is slightly different from the Indonesian trials. But the interesting part for this for us is also learning how to use our eye feeder in conditions where we have this kind of huge amount of aeration inside the pond. They introduced additional sound. But we are learning actually how to manage this sound as well as still be able to extract important information from the sound. Okay, so for the eye feeder results, basically in the Vietnam farm trial, the eye feeder actually totally harvested. So our 2 ponds each, theirs, 2 ponds ours, we average out the results. Our pond, eye feeder pond, harvested about 2.8 tons. The technician ponds harvested about 1.7 tons. So there's a total about a ton improvement, about 70% improvement. The FCR, our eye feeder average is 1.69. The technician ponds were 2.1. Okay. So there's a improvement about 22%. The average survival rate, ours is 74%, and theirs about 56%. So a 31% improvement. The average mean body weight, ours is at 15 grams, theirs about 12 grams. So about 23% improvement. Productivity, likewise, ours is 2.8 kg per square meters, theirs is 1.7 kg per square meter. So about 70% improvement. The most important part actually is the revenue. Actually, the revenue for this trial with Vietwook, our ponds, the total revenue we took out from the pond is $1,800 US, $8,100 US, whereas the Vietwook ponds were at about half that value, which is about $4,000 US, so about 99% improvement. So if you look at the overall results, we separated the streams into 2 portions because the Vietwook manager told us that if the streams are typically grow in 1 pond, and then they will transfer the streams to another pond as they grow bigger to spread out the streams, right? So there is 2 batches. One is the original streams which are originally in the pond. The other one is the one that we split out and transfer into another pond. So what they told us was that the transferred streams typically will have worse production output than the original ponds. So for this trial, actually, if you look at it, if we compare the original ponds, their original pond and our original pond, the overall MBW, actually, our ponds are better, higher in MBW. And the transferred PON is even clearer. Our PONs are actually have more MBW than have a higher MBW than their transferred PON. So if you just compare FCR and MBW, basically the eye feeder is okay. I put in these boxes because it helps to kind of better see the results, to cluster them. So if you look at our eye feeder PONs, the one with the star mark, actually our results are quite consistent. We are producing better results than theirs. And typically you see that their results are a bit scattered and less consistent with ours. Okay, if you look at productivity, FCR versus productivity, also our results are consistently way at the left top region, where theirs is a bit spread out and inconsistent as well. So these slides we'll provide to you later after the training, so you can also take a look at it. So the Indonesia ponds, for this trial, actually we did outdoor ponds, 4 ponds for the eye feeder and 4 ponds for the technician. So G2 to G5 is eye feeder, G7 to G10 is the technician ponds. The density typically for all the ponds are about 130 pieces per square meter on average. Yeah. The design of the ponds were specifically positioned because this is the kind of the traditional setup that we're used to, not like the Vietwood one. So typically we place the hydrophone downstream, and we also control the feeding area. So in this particular trial, the overall setup is more familiar with us because we didn't use any diffusers or anything like this. But outdoor pond means rain shine will affect the harvest as well. So if you look at the results, the eye feeder ponds in total harvested 17 tons from all 4 ponds, and then the technician ponds were about 14 tons. So there's about 23.8% improvement. The FCR again, we have a 5% improvement. Ours at 1.57, theirs about 1.65. If we look at the survival rate, it's about 11.3% improvement. Ours at 69%, theirs at 62. On average, our eye feeder ponds are about 4 grams larger, so about 20% improvement. In terms of productivity, we are at about 25% improvement. And then revenue, of course, again, we age them out, but in this time, depending on the culturing and the capability of the technician, of course, and the pond setup, we only achieved about 8.9% improvement, but still significant. So for the Indonesia ponds, we actually split out 2 batches, batch A and B, which we have shared with you all before. And in batch A, if you look at the overall MBW improvement comparison, actually is more or less similar. It's quite the same. But if you look at batch B, the eye feeder results are better, much better than the technicians' streams. Okay, so we typically have a higher and bigger MBW. Okay, so if you compare FCR and mean body weight, you find that actually all 4 ponds, the eye feeder ponds, are quite consistently clustered at the upper left corner. First of all, it's consistency. We produce bigger streams, lesser FCR, and then compared to the technician results, which are typically more scattered. Okay, this again shows the same patterns as the ones in Vietnam. Then if you look at FCR versus productivity, you also see that the eye feeder results typically are clustered on the top left, which are good, consistent results. Whereas if you look at the technician results, they are also up and down in terms of their productivity. So in Singapore, the results okay, for Singapore, it's slightly different from Indonesia and Vietnam. In the trials that we did in Singapore, we did typically in smaller ponds. So this result we took from one comparison, but it's not done in the same time. We compared the pond that they did before, they did in their own culturing by hand feeding, and then the same pond, we compare our results that was done on the same pond together with them, but on a separate trial. Okay, the reason why for Tianhu is different is because the setup is also different. They have their own RAS systems. The water parameters are different because the RAS requires that the salinity be at certain levels. And also the different trials we did with them, we trialed growing the streams at different salinity levels, also from 5 ppt all the way to 16 ppt. Yeah. So, but for this particular trial that we did, the water parameters are about the same, 16 ppt salinity. The only difference is, of course, the results. The total harvest that we took out of the eye feeder was 325 kg. They did about 178 kg, so that's an 82% improvement. The FCR, we did about 1.2, 1.3 FCR. Theirs about 2.2 FCR, which is about 43% improvement. The SR is significantly different. Ours is 72%, that's 30%, so about 240% difference. The only in this particular comparison, the only thing that we didn't match is the MVW. They were able to get 30 gram streams at the expense of survival rate, but ours is at about 25 grams. Productivity-wise, we achieved, the eye feeder ponds achieved 9 kg per square meter, and the manual ponds achieved about 5 kg per square meter, so about 82% improvement. So for this 9 kg per square meter results that we have done with Tianhu, it's not a one-time result. We actually repeated it 3 times with them. Yeah. So the eye feeder solution, I think most of you have this misconception that the eye feeder comes with a submerged sensor, but actually the eye feeder doesn't need to come with a submerged sensor. There are 4 different ways of using our eye feeder. The first one is actually eye feeder with no sensors. So with no sensor, it has automated feeding, means we connect to the feeder and the eye feeder do the feeding. Because there is no sensor, we do not stop feeding based on DO levels. Okay, that's one difference. If there's no sensor, the eye feeder will not has no mechanism to stop if it drops below a certain DO level. Okay, the real-time analytics will be done via StreamTalk. The second one is that we can combine and run with the eye feeder is use the RDO blue sensor, which is the DO sensor. In this case, it will do automated feeding, and we can set the threshold for the DO levels. If it falls below a certain DO level, the eye feeder will stop feeding. Okay, this is the same with the AT500. If the eye feeder is deployed with the AT500, same thing. We will be able to automate the feeding. We'll be able to stop if there's a DO threshold set for the pond. All the analysis will be done via StreamTalk. Okay, so the last one is StreamTalk. StreamTalk, there is no automated feeding. For this, we only deploy the hydrophone. We do not connect to the feeder, but we encourage the farmer to actually consider connecting their feeder to our panel so that they can use our timer feeder features. Because when they do that, we can easily integrate the analysis and they can get a better understanding of what's happening in the stream pond. Yeah, so that's the general results and the different permutations of the deployment of the eye feeder that is feasible, that's possible. Now we want to hand over to the team to talk about the SOP, and also the individual parts. So we'll go into quite a bit of details in terms of the hardware and the software and the analysis itself.
Okay, so for the installation and iFeeder deployment, we will go through the SOP first, and then, yeah. So for first, we will get the farm to fill the pre-attached pre-deployment, and then we prepare the deployment with the needed hardware. So usually for this part, the setup include basic check for the component and in the panel, and also the detail setup can refer to the, later on you can refer to the, to the document that I attached here. And then complete the FAT checklist before ship out the panel. And then we arrange the panel shipping and transport to the farm site. So once the panels arrive, then we will proceed with the site deployment and complete the post-deployment checklist. And contact the local IT engineer if they have, or coordinate with SG team to tune the hydrophone. And then after that, we need to complete the feed dispense rate test report and complete the SAT checklist. For the panel and hydrophone setup, based on the following layout guide. And after that, we can start the daily operation and need to complete the daily report. So in all projects, in order to follow up the progress, we will set up 1 hour weekly call, and then at the end of the project, we will write out a final report.
Okay, so this SOP is documented in a Dockerpedia site. I think all of you should have access to the Dockerpedia site. You can actually look at the SOP, all the checklists, all the reports, including all the procedure and steps, and what to check for the hardware and software are all documented there in detail. So you should be able to have a good reference from the SOP.
Okay, so next for the roles and responsibility, I will pass to my team. This will cover from AI introduction by Looming and water quality monitor, farm operation consultation by me, iFeeder operation by Steven, and iFeeder stream talk system working theory by Trisha.
Okay guys, good morning. Can you hear me?
Yeah.
Okay.
Oh, Looming. Hello.
So I'll be sharing on this hardware portion. So we'll go over a few subtopics like overview and all the components, panel, feeder, hydrophone, the physical sensor, and then lastly the installation and the testing part. So for the overview, very simple things. Our panel is actually designed to run 4 ponds. So 1 panel, 4 ponds. And we are having a plan to upgrade it to 8 ponds per panel, still in progress, still in testing. So for now, it's still 4 ponds. So the main function of this panel is actually just to receive the hydrophone signal and then trigger the feeder to feed based on the sound signal, based on our AI. Then the other thing which is important is the internet connectivity that we have. We can make it through SIM card or Wi-Fi. So this is the basic layout that you will see in the panel. Some of it may change time from time, but the layout will be like this. So the first one, the top left one, is the circuit protection devices. Basically, it protect the panels. You don't need to know the details. Then the second component is you see the second row, the feeder control module. So basically these are control modules. You don't need to know the name, you cannot remember. So the bottom part is actually the cable connection point. So basically you connect all your power supply to the panel, power supply to the feeder, the sensor cable is all here. Then on the right side, the blue color thing is actually the router that provides the internet connectivity. You can put your SIM card inside here and you can use it to connect to Wi-Fi also. And you will bring the industrial PC online. So the right one is the industrial PC. Basically, this is the most important thing. Our program AI is all in this. Wait. Never mind. Okay.
Yes, my mouse.
Okay, the last thing is the sound amplifier. and we call it sound card also. So this guy basically amplify the hydrophone signal so that our IPC can see properly, can listen properly to signals. Oh, like someone moving. Okay, the next component is the feeder. So feeder is selected based on the pawn layout and the size. So every farm might use different feeder. So we actually don't want to control this feeder selection. So this can be either provided by Aqua-Easy or the customer themselves. So the only basic requirement for the feeder is the power rating for it. So it must be using single phase. So 220 to 230 AC, which is common in Indonesia, Vietnam, and Singapore. And then the other thing which is important is actually the accuracy. We want the dispense rate to be consistency. So standard deviation should not be more than 10 gram. For now, this is still very hard to achieve with wet feed. Dry feed is still okay. So we'll go along with the project or the discussion on this thing. The next slide. So the next one is the hydrophone. You see the picture, the black round thing is the hydrophone, and with its all cabling. So the main function is the capturing the sound signal under the pond. Currently the length limit is within 50 meters, and we have a plan to extend it to a maximum of 150 meters. So still in testing progress. And the next thing is the physical sensor. This is for water monitoring. I think most of you is more familiar than me at T500. So this now is optional to the customer with different pricing. So whether when they purchase these eye feeders, they want to use this sensor or not, they decide it. So the main function is actually to check the low DO when we are running the eye feeder. So to cut off the feeding when the DO threshold is low. So if they don't choose to use this, the customer must take care of the DO themselves. And as we go into installation, some simple things. Because all these details you can actually find in the detailed deployment documents that just now Lucia showed. So I'll just go through simple one. So the most important thing is actually your panel positions. So ideally we want to put into the center of 4 pawns, like this layout for an example. But you have to take care of the cable limit of this 50 meters. You must make sure where you want to put your hydrophone, your sensor is within 50 meters. Then the other thing is the telco and Wi-Fi coverage. Basically, you want to test your SIM card first if your signal is good here, because we actually need a good internet to run things properly. And then the next thing you do, you lay the cables. After you lay the cables, connect the cables, and then you set out your instrument, the hydrophone, the physical sensors, all the details in the documents. And then the last part, after you set up all these things, you want to test your panel. So these are a few things we run through every time. So the first thing must be the internet connectivity, so that our team from Singapore can help you remotely with all the connections. So the next one is the feeder dispense test. So basically, this one is just to test that the connection between the panel to the feeder is okay. When we run it, the feeder can turn. That's it. The detail on the dispense rate testing will be covered later. Then the next one, we want to check the hydrophone sounds. This one, you also require the SG team to help you. Then the next one is the physical sensor data availability. If they opted for this package, we will need to check the sensors data also. It's automatically coming in after setup. And the last thing is the power failure check. Basically, we will trip the panel and see if the panel can restart on themselves, and every program is running back automatically. And also the UPS function. We have a UPS for the panels. So when we trip the panel, the UPS should turn on and continue the panel functions until it die out. Normally a UPS, I think at most it can run 30 minutes. That's the most. So I think that's it on the hardware part. I will pass the mic to Lucia.
Okay, so next for the farm operation consultation. So basically, from my side, what I did every day, I visit farm and identify the problem on the ground. For example, we use different feeder and also summer sensor. So I just identify the problem and also sometimes they need maintenance. And I also did a daily routine such as monitor shrimp and water condition. Check the physical quality reading, either it's within range or we got like sometimes our sensor got problem, like need to change port or need to clean. And also check the auto feeder. This one is actually very important. Every day I always make sure that feed dispense out from auto feeder. And I also did feed tray check. This feed tray, I depends on condition, but for this one actually used to observe shrimp condition, either a disease sign or shrimp in a good condition or not. And also other than that, I used to check the feed amount that being dispensed by our auto feeder to prevent overfeeding or underfeeding. So this is the example of the shrimp and water condition. So every day after I observe, right, for example, shrimp got disease or soft shell or like this pond condition, you see, what is it, the dolomite precipitate and also a lot of bubbles. So I will always feedback to operator and settle this problem.
Yeah, so for what Lucia shared with you all, basically we are looking at, for example, Sifa and Tuat, your team, your guys on the ground, to actually also help us look at some of these things that Ruzia has shared. She manages the farms here in Singapore, but in Indonesia and Vietnam, we also depend on your guys to feed this kind of information to us so that we know what is happening there when we're not running everything blind here. When we start trials and when we have productions in the other countries.
Okay, next I will pass to Stephen for iFeeder operation.
Okay, hello, I'm Stephen. I'll be covering, I'm the, Ibrahim, sorry. Okay, my name is Stephen, I'm the data engineer. My job scope is more on the technical side of what Rosia does. I check on the feeding of the shrimp, the response, and also monitor parameters and check if the system do the setup of the technical software side of the iFeeder system. So I'm going to do a brief overview of the iFeeder system, talk about the gateway configuration setup and the feeding table. So traditional feeding strategies are based on use of feeding tray to estimate the shrimp hunger. This is what Rosia mentioned earlier. iFeeder uses a hydrophone, which is the underwater microphone, to analyze the sound of the shrimp pond and identify the shrimp feeding responses in real time. So this allows us to respond faster to any issues in the pond. And we also measure it consistently, as opposed to you have to manually start the feed tray tests and then find out the response. So we take the raw sound from the hydrophone to get shrimp activity number index and log file. And we also will schedule the feed automatically based on the feed start time, end time, recommended feeding amount, and dispense feeding amount. The recommended feeding amount is generated by the feeding table, which I'll go into later. But it's a fairly simple problem for this scheduled feeding. If I'm feeding a certain amount and each time I dispense is say 1 kg of feed, it will calculate basically how often I need to dispense feed in order to meet the scheduled amount of feed. And when the feeder dispense feed in the pond, the iFeeder will know it that you dispense feed, and you analyze the response to feed and adjust it accordingly in the log file. The log file looks something like this. Can you click on this?
Yeah.
No, I mean a link. Can you? All right. Will not be. Why did not be the red dot?
I think it's in here.
Okay. No.
Okay. You see.
Oh. Okay, sorry. This. Can you all see this? Log file?
No. No. I cannot see it.
Maybe you have to change the screen sharing to the log file.
Are you screen share?
Yes, screen share.
Share again.
Oh, she's
Yeah.
sharing the document only, not the screen.
Can you see the log file now?
Yes.
Okay. So this is what the log file looks like, and is it the most? Yeah, this. Sorry.
You stop first. You stop first. You stop sharing.
Okay, no. Here I got it. So this is what the log file looks like, and it's basically all the sound responses for the whole day, one whole day. Okay, so more in depth. Okay, in more in depth a little bit. This is the log file. As you saw earlier, it had a timestamp here. And this is basically a timestamp, and the noise level, and the raw noise. So sometimes if you see when we're doing feeding dispense test, I say there's no noise. I'm referring to the noise level here being 0. The noise level. It's the noise level. Okay. The noise level can go from 0 to 9. Okay, there are basically nine levels. Low is 1, low medium is 2, low high is 3, medium low is 4, medium is 5, medium high is level 6, and high low, high medium, high is 7, 8, 9 respectively. I think you all can get the idea. Any questions so far?
Why do we need the text and the label number? Why don't we use one?
The noise level helps us. The raw noise is the raw sound information. It has more information than the noise level. The noise level is useful for doing analysis.
I mean, why we need the text and the number ML or ML for number 4?
Yeah, so the ML and the LL and LM and all this is actually for labeling purposes. Yeah, it's for grouping and labeling purposes. The number is used as a means to do quick calculations, faster calculations, rather than we do text comparisons.
Oh, okay.
So it's a bit technical detail, yeah. But they somewhat serve different purposes.
Okay.
Excuse me, I have a question.
Yeah.
In this the noise level, which level is the acceptable or the good response from stream?
Okay, when we are talking about response, okay. My next slide we'll try and explain a bit more on that. Okay, this is a plot of the raw noise here against the timestamp. So the graph, if you plot it, it looks something like this. The red lines is when you dispense feed, and the blue line is the noise that it was in the log file earlier. So the red line, you can see every time I dispense feed, the noise goes up. And this is basically the ideal I want to see. So it's not so much that the level must go up to a certain level, but there must be a clear response to the feed. That's what I want to see when I do the feeding tests.
So regarding your question,
This is
who asked that question? How or no?
Yeah, me, how?
Oh, okay. So basically what we do is during the tuning, we set this baseline. You see this baseline?
Yes.
Yeah, so what we do is during tuning, we set a baseline to get the average sound in the water. You can look at it as average sound in the water. What happens is that when we dispense feed in the water, the streams will react differently from the baseline. And this is the important information that we want to capture. This spike information is what we want to capture. Yeah. So if they behave normally and there are no exceptional behaviors or anything like this, we should see this standard baseline like this. Later, Chu Si will talk a bit more and show you a bit more graph so that you get a picture of what the system does.
Yes, understand. But as which noise or expect noise level that we receive from the system, or which noise expect noise level we can receive from the stream when the system work well, and which one is the bad signal from stream?
okay. Next slide will have a bit more. Okay. So this is this is a more normal. Okay, this is a normal, good, more common feeding pattern. You can see early in the morning when I feed, the spikes are very high, and there's burst feed. Okay, you can see that there's more red lines. We are giving more feed. Towards the afternoon, the feeding response goes down because the shrimp are more full, so they eat less. And we also, the system iFeeder also reduces the feed given. And towards the evening, the shrimp are hungry because in the afternoon they eat less, so there's more response to feed. This is a more common feeding response. This is an example of not good feeding response. You can see in the early morning, it looks normal. You see feed response, but after around before 9 o'clock, the noise becomes very high. The shrimp are very active. This could be either possibly because of molting or other possible reasons. But this is an example of a bad response of shrimp. There's something going on in the pond. This is the other extreme of bad response we don't want to see. You can see when I feed the red lines, I dispense feed, but the shrimp don't respond. The spikes are very small or non-existent. So this is another example of a bad response of shrimp. Does that answer your question?
So for the laboring portion, typically when we do the tuning, we will tune between 2 to 3. So you remember earlier Stephen showed you the table on the labels. So typically we will try to tune it to 2 to 3, and anything that's higher than 4 is considered bad. When you say higher, means that you go back to the poor feeding. When we say higher, it means that it's consistently higher. It doesn't come down, for example. It's not like the normal feeding. See, it just keeps going high. It means they're going crazy inside the pond. Okay. Sorry. So if it's a normal feeding, typically if you look at it right, they'll have when the feed is thrown, they'll have a feeding frenzy, but their behavior will go back to normal again. Will drop back to normal again. But if they consistently remain high, then typically something is wrong because they are typically going through some stress instance or situation. What is happening there, we don't know because there are a lot of complexity in the water. We only know that they are behaving abnormally. So if they typically stay between 2 to 4, the label that we set 2 to 4, typically they are okay, they are normal. And every time we feed, we should see the feeding frenzy behavior, that spike that we want to see. So if we feed and there's no spike, it's also another problem because they are not responding to the feed. Either there's not enough streams or they are hiding somewhere and they're not feeding as we want them to feed. Does that answer your question?
Hi, Evan and Stephen. I just have a question. When you talk about like the feeding response level, like 3 and 4 are under expected ones. So what, in case like what if for example some background noise at this and they have the same level with that feeding response level that we expected, how do we know and how do we filter out that?
Okay, so the baseline is not so important. It's actually the reaction to the feeding that is important. So what we do is in the tuning portion, what we do is we set the baseline. Once we set the baseline, we use this feed dispense test to test the reaction, and that is the important portion.
Did I set the basic or the base level first? Right.
Yeah.
I think what asking is the noise. The noise we actually already offset when we do the baseline tuning. It's asking where the noise coming.
Okay, so this is also a little bit of the challenging part. It depends on the setup of the pond. For example, like the Indonesian ponds where they just use standard aerators. This baseline has a more meaningful score because we don't have additional complexity in the pond. But if you look at the Vietbook 1, there is possibility of interference also from the diffusers and all that. That is correct. But what we want to capture is the reaction of the streams when the feed is dispensed in the water. That is the more important information that we want to capture rather than the baseline noise, because the baseline noise is which is more like trying to set a consistent value that we can measure against.
So another question is just to confirm again about the concept of the eye feeders feeding. Like normally, like for the first feeding, for the first feed dispense, like we will dispense the feed first and get the stream response, or we get the stream response and then we delete then we dispense the feed. Just to confirm.
How about we explain, finish, and once we do, if you still have questions, we can ask again at the end of the session.
Yeah, I think let's move forward because there's a lot more information coming, and we go through first, and then we can come back to some of your questions later.
Okay.
Okay, so here is the basic flowchart of how the eye feeder works. First, the eye feeder will check the noise level of the shrimp pond. If the noise level is very high or very low, the eye feeder skips feed. Being very high means that there's a lot of activity in the shrimp pond. The shrimp are having a lot of activity, and it's possibly a sign of something is going on. Very low is the opposite. There's very little activity in the pond, and eye feeder might also skip feed in that case. If the noise level is normal, the eye feeder will dispense feed, and the eye feeder will check the noise response to feed. If the noise response to the feed is extremely good, the eye feeder will trigger a burst feed. If the noise response to feed is good, just like normal good response, it will just proceed as normal. It will dispense the feed and carry on. But if the noise response to the feed is poor, this is I dispense, I don't see a response to the feed, I will skip the next scheduled feed.
Not you or the system.
The system eye feeder will skip the next scheduled feed.
So Stephen is not sitting behind the eye feeder controlling the feeding. Don't get it wrong. You always use the wrong words.
I'm sorry. It is not me. It's eye feeder will skip the next scheduled feed. There's also something I forgot to go over through earlier about the scheduled feed. To schedule the feed automatically, you need to know the amount of feed dispensed in the feeder per throw, and you need to do a dispense rate test to calculate, to find out this amount for each feeder. We strongly recommend you do this for each feeder, because even if the model of the feeder is the same and the feed is the same, the dispense amount can be different for each feeder. Okay, so the process for doing this is you fill the feeder with feed. The amount of feed in the feeder will affect the dispense rate. If there's a lot of feed in the feeder, the pressure will cause more feed to come out when you dispense. So we recommend filling the feed at least one bag of feed to simulate actual shrimp pond conditions. Trigger the feed for the time. You can do it for certain 30 seconds, 60 seconds, 80 seconds, and you record the amount of feed dispensed. And repeat at least 3 times. You can take the average of the feed dispensed, and there's a table. The table is, it looks something like this. Excel sheet. Something like this. For feed type A, maybe 33 seconds, how many grams and how many grams per second? You repeat this 5 times or however many times, and you get the X. So this is basically the process of doing the feed dispense tests. After you do this, you set the feed dispense, the seconds that you want to set the feeder for, and you choose that based on the feed dispense per throw. Our experience is if the feed dispense per throw is very small, the shrimp size variation will be very large. We think it's because alpha shrimp in the pond will eat all the feed there, and there won't be enough feed for the small other shrimp to eat. So there'll be a large size variation in the pond, and this will just grow bigger over time. But if the feed dispense per throw is too big, too large, you can get overfeeding very easily. So this will, if you overfeed, there'll be problems in the shrimp pond because there's too much feed in the water. The feed will decompose, it will use oxygen, it will reduce water quality, and there'll be issues. So the feed dispense per throw should be.
Okay, so what Stephen wants to say here is that for the throw per dispense, right, need to be large enough, not too much and also not too little. This dispense amount typically is we estimate and calculate on our side to adjust it so that we get reasonably amount of feed so that we can get the right reactions and also enough amount of shrimps to get enough feed to cause a reaction.
So we need to do for the different feed type also, right? I mean the size of the pellet.
Yes, different feed types will have different feed dispense amounts.
Okay. And maybe also the same for the nutrient mixed feed also.
Yes.
By right, we should also actually do a dispense rate for the nutrient feed because this is also important.
Whatever the farm use,
Yeah.
we need to do this test.
Until the day we can find a feeder that we know for sure can give us the amount of feed that we want specifically, we have to do these trials.
Then if they do like nutrient mix feed like someday, and then they do the right feed for someday, then we from outside we need to update the dispense rate on the apps frequently, right?
Yes. Yes. Okay. Next thing I'm going to talk about is the hydrophone location. We want to put the hydrophone so that it can record the response of the shrimp to feed. Because if we cannot detect the response of the shrimp to feed, we cannot adjust the feed dispense appropriately. So from past experience, hydrophone should be at least 5 meters away from paddle wheels in the auto feeding area, and the hydrophone should be facing the auto feeder directly. So here is an example in a round pond where there is paddle wheels causing there to be a circular water current, a clockwise water current in this case. We want the hydrophone, we have this green dot, this is the auto feeder, and auto feeder dispenses feed in this white area. The hydrophone should be inside the feeding area. Specifically, it should be where the feed is thrown the most around there. So, for example, if the hydrophone, if the auto feeder dispenses a lot of feed around the circumference at the edges of the circle, the hydrophone should be in that area as well. The other thing is the hydrophone should be downstream from the water of the auto feeder, so that when the water current will move the feed around, we want the water current to move the feed towards the hydrophone and not away from hydrophone. So if the hydrophone is on this side of the auto feeder, the current will push all the feed away, and this will affect we won't be able to get such a good feeding response.
Okay.
In a square pond, this example of square pond is similar. The hydrophone should be in the feeding area, and the water current should push the feed away towards the hydrophone. If we zoom in, the hydrophone it look like this. I think most of you have also familiar with this. This large flat surface should be is the side that actually picks up sound. So this surface should face the auto feeding area. Also note that because the hydrophone the cable currently is only 50 meters long, the location of the hydrophone must be within 50 meters of the control panel. The last thing I want to talk about is the gateway configuration. This is just some basic information about how to make changes, basic changes of the auto feeder, iFeeder, sorry. So to access it, you log into the website, the app.aquaeasy.live, and go to the gateway configuration tab. It's over here. After you go inside, the page will look like this, and you select the panel that you're interested in. After selecting the panel, you get the panel tag. You select the pawn tag, and you will start in the feeder sub tab. It will look like this. So if you scroll down, you can see all the settings. So here is just basic information. Here is the where we fit in the start hour in a 24-hour clock. So 7 is 7 a.m. This is the feeding window in percentage of the day. The feeding window is the percentage is a set hours, is a set time where the feed will be dispensed. So 66% is basically about almost 8 hours, 7 hours, sorry. It's almost 16 hours, about 15 hours, 40 minutes of the day. And after, that means 15 hours, 40 minutes after 7 a.m., the feed will stop. And here is where you turn the feeding on and off. These are the things you use most commonly. At the tab at the end is the feed table tab. We use this to update the feed tables. So the feed table is in a CSV format. It looks something like this. Okay, a table with DOC and feed. So for DOC 45, the feed given is 63.52 kg. The feed here is in kg. And it's a table for all the DOCs that the shrimp cycle is. So the feed, you can see the feed increases every day. And you can also review, there's a text box here, the uploaded feed table or the current existing feed table. You can see it here. You can scroll down and see it. And if you want, you can make changes. After you make changes, you scroll down and you save. You click submit, and it will be uploaded.
Hi, Steven. Can you explain again what is the feeding windows in percentage? I don't understand that.
Kyushu will go through that again as well in more detail later. So
Okay.
The last thing is the advanced gateway configuration settings. So if you click the advanced tab here, you will see all the pawns in the panel, and you can select either test feeding or auto wiping. So if you click test feeding, you will manually trigger a test feed in the pawn. So we use this normally to see that the feeder system will trigger feed this properly and that feed comes out of the feeder properly. There's no blockage. And also when we are doing hydrophone, we're doing the hydrophone feed response test. So I dispense a feed from the iFeeder, and I see the response of the shrimp in the hydrophone. If I see if I can detect a feeding frenzy, that means the location of hydrophone is good and the setup is good. The other setting here is the auto wiper, I think. This triggers one round of the physical sensor cleaning. And it's used to clean the physical sensor. If you don't get, if the DO is low, I suspect it's because the physical sensor has algae or something blocking on it. You can go into this tab, you click auto wiping, you click multiple times to trigger it to click in, and you see there's the DO reading improves. So that's the advanced tab. Now Tusha will talk about this. Hand over to Tusha.
Okay. Okay, now I will introduce about how iFeeder works and how ShrimpTalk works. Okay, first let's review how iFeeder works. So this is a flow chart. First, the shrimps generate some sound, then hydrophone capture the sound. After we capture the sound, we will do some processing to transfer the raw signal to some processed signal. So this processed signal is very important for us. This processed signal will be input into the AI engine. The AI engine will decide how to control the feeder to dispense food. The food actually can be chosen by different types, different brands, different manufacturers. So the important thing I want to highlight here is iFeeder works based on the processed signal to make decision how to feed the shrimps. So once you understand the signal, you will understand how iFeeder works. So later I will explain this processed signal. Okay. So first, let's see some very normal signal. So this signal is with no feeding activity. From the times you can see this is a processed signal from midnight, 12 o'clock to 9 a.m. This is from 12 o'clock to the midnight to the next day. So during this period, there is no feeding. And if the shrimps are healthy, you see the hydrophone signal is stable and stay at the low level. So this is a normal signal. Nothing happened. Shrimps are healthy. No feeding activity. This is a raw signal. Okay. Then now we see some signal with normal feeding activity. Please here is normal feeding activity. It's just like the shrimps response normally. So you see from the very calm low level signal, once we dispense some feed into the pond, then the shrimps can give us some response. They are capturing the feed, they are eating the feed, then you can see the spikes every time. So this, you see every time when we dispense feed, there is some spike appear on the hydrophone signal. So this spike is some the shrimp's response to the feed. Okay. Now in the last slide you see we have some regular feeding amount. So previously Stephen have introduced how to configure the gateway to configure iFeeder. So I want to highlight there are three parameters. Three parameters are very important and need to be configured. So the first is the start hour in the gateway here. This parameter decides when is the first feed be dispensed. Once you configure these parameters, the first feed will be dispensed at exactly the time you configured. We don't consider any hydrophone signal, we just dispense one time. So this is a kind of initial dispense. The next is a percentage day is here. So this percentage can be from 0% to 100%. So this percentage decides how long the feeding window. So I give an example to answer the question the Tua just asked. So for example, if we setting here is 66%, we need to multiply the 24 hours per day. Then we know the feeding period will be roughly 15.84 hours. So this is the total feeding hours for today. Then iFeeder, as we have decided the start hour at 7 a.m., then iFeeder will start at 7 a.m. Plus 15.84 hours. If the ending time is roughly at the 10 p.m. 50 minutes. So this is how we control the iFeeder stop feeding during the day. So this is these two parameters. After we setting these two parameters, we got the feeding window for the day. The third parameter is the feed quantity we configure here. So this is why we need to do the dispensary test. So this is also control the feeding schedule. So for example, today we plan to feed 50 kg for the whole day. Then if the feed quantity is 1.13 kg for one time dispense, then the iFeeder will dispense roughly 44 times. So you will see if nothing happens, if just a regular feeding, you will see 44 the peak spikes. So the interval between two dispense is roughly 22 minutes. So this is just a mathematical calculation. So these three parameters are very important to configure the iFeeder work properly. Okay, if we just run iFeeder using the three parameters, it's like timer feeder, but actually iFeeder is more smart. You can see here, every time we will detect the shrimp's response. So if the shrimp's response to the schedule feeding is high, it means this spike value compared to the baseline, if the difference is very high, then one more feed will be followed by the schedule feeding, the boost feeding. So you see, in this time, the schedule feeding, we got a high shrimp response. Then we add one more boost feeding. So you can see the 2 consecutive spikes. So this is one iFeeder will control the feed based on the shrimp's response. So once we detect the shrimps are actively respond to feed, we will add one boost feeding. Next slide. Another feature of iFeeder is that if we cannot detect the shrimp's response to the feeding, for example, you see the red line is we dispense feed. The blue line actually is also we plan to dispense feed based on our schedule. But you see the signal every time we dispense feed, actually the response is not very strong. It means we don't know why the shrimp, maybe they are full already, or they don't have appetite. Then the next time we will cancel the scheduled feeding, we'll skip. So no food will be dispensed. So if you see during the period, we dispense one scheduled feed, then skip one time. So this is how iFeeder control the feeding by using scap feeding. This is the 2 features, boost feeding and scap feeding. Okay. So the next important thing is that iFeeder will not add boosting or skip feeding unrestrictedly. So we set some limitation or set some regulation to control the boosting and the skip feeding. So Stephen have introduced the feeding table. So we know the planned daily feeding amount for the day. Then the maximum boost feeding amount can be configured at roughly 20% of the daily feeding, or 10% or 30%. This percentage can be configurable. Based on our experience, roughly we set at 20%. This value can also be changed based on the farmer preference. For example, if the farmer want the shrimps grow fast, they don't care about the mortality, this percentage can set in 30 or 40%. But if the farmer say, okay, I need to harvest more shrimps, I care about the survival rate, this booster percentage can be lower than 5% or 10%. To use this one, we can cap the daily feeding amount at, for example, here is 120% of the daily feeding amount for the feeding table. This is the cap for the boosting feeding. Then for the skip feeding, the number of skip after one scheduled feeding can also be configured. Usually we set at one time. So if you see, can you last slide? Previous one.
Previous.
Yes. So you can see here, after one scheduled feeding, we skip one time. Actually, we can configure skip 2 times or 3 times based on the farmer's preference. So if you skip one time, at most 50% of daily feeding can be skipped. If you set this value more times, then more feeding can skip. So this is configured by farmer or our technician. But based on our experience, we're setting this value as 1 time. So you don't need to worry about this. All this percentage skip times, we have some default setting based on our experience. So you can just run as default model. If the farmer be familiar with iFeeder or the technician be familiar with iFeeder, after several trials, they can tune these parameters to get the better performance.
Chusei, I have a question, Chusei.
Okay.
Can you go back to the previous slide?
Okay.
Yeah. When you said like the next schedule feeding will be skipped, so it's mean like a slide before you said is like our feeding frequency, like maybe interval, maybe like every 22 minutes. So it's mean the next schedule feeding is the next 22 minutes, right?
Yes, right.
Okay.
So for example, this time I dispense feed, then after 22 minutes, it's a scheduled feeding. If I decided to skip, there will be no feeding into the pond. You need to wait another 22 minutes for the next schedule. So the total is 44 minutes.
Okay. And normally we just skip like once.
Yes. If you skip 2 times, then roughly maybe 1 hour no feed in the pond.
So we've observed different feeding patterns in different ponds, right? Some ponds actually in the morning there's a lot of bursting, and then in the afternoon the feeding will slow down, and then in the evening they'll pick back up. Sometimes in the morning they don't feed at all. There's a lot of skipping, but in the middle of the day they start picking up. The next day in the middle of the day they start picking up their feeding again. So there is no the boosting and the skipping. There's no fixed control. It just depends on the reaction of the shrimp to the feed.
So is that correct to say like our eye feeding concept is for the like when we say like on demand feeding is for more area feeding, right? But in general, in the total feeding amount is still under our control, right?
Actually, the total feeding amount is not under our control because it depends on the reaction of the shrimps in the water. But what we do prevent tragedy from happening. We put in a feeding table so that we can ensure some amount of feed in the water to guide the eye feeder.
Just to add, you can understand in this way. So the daily feeding amount, actually eye feeder have a range, like we have a minimum and a maximum. But the actual feeding amount, this value we don't know. We let the shrimp to decide based on the demand. But we have a range.
And we can control that range.
Yes, we can control the range.
So the range.
We can avoid some extreme scenario.
So the range is to also to help us control the overfeeding, right?
Yes. We cannot let the shrimp too hungry or too full, something.
Because we also realize that there are scenarios when actually the shrimps keeps feeding, but actually the output of the increased feeding actually is not optimal at all. Yeah. So this is how we have figured out how we have currently determined how to optimize the feeding. Yeah.
Okay. Then this case, I think to have a good and accurate feeding table is very important. I think that also.
That's where Chu-Si is coming to.
Yeah. Okay, let's go to the next slide.
Okay.
Then I will introduce how to generate the feeding table. I think that's why you want to know this. So first, I introduce some traditional way. I think most of the farmer or technician use some function. For example, here is like you use MBW, multiply the stocking numbers, multiply the survival rate, multiply the feeding ratio, then got the daily feeding amount. This is the traditional way. And I think they have this table, and based on the value, they can calculate roughly the daily feeding amount. And some functions may also consider the DOC as an input when they calculate the daily feeding amount. We see in Vietnam, they have some feeding table based on the DOC values. So, and also, of course, each farmer have some secret, they have some their own recipe to calculate this kind of feeding amount. So this is the traditional way. Now, eye feeder, we change this. We never calculate based on function. We calculate based on the machine learning model. So you can see here we have a machine learning model. Every time you want to calculate a feeding table, we need some input. The first input is the MBW measurement. So from the first measurement to the last measurement, no matter how many times, we put all this data into the machine learning model. So this MBW measurement is always very important for us. So that's why we are always chasing the farmer to do MBW measurement and must be very precisely, because this will impact the feeding amount. The next input is a stocking number. So we need to know the initial stocking density. If the stocking number is quite different from the true number in the pond, it also will impact the feeding table. The third one is mortality. So once any mortality happened in the pond, for sure some shrimps died. So we don't need to feed them. So we must input this value into the machine learning model as well. After you input all these required values into the model will output the feeding table. So each DOC, how many kgs we need in the pound. Okay, next slide. So I will introduce more detail about how the machine learning model works. You can see first from the graph, you can see some green dots and a curve, the blue curve. So first, let's focus on the curve, the blue curve. Actually, the machine learning model is calculate the feeding amount based on the curve. For example, in the curve X, Y is the MBW of the stream size, and the Y-axis is the daily feeding for 10K streams. If the daily feeding is how many kg for 10K streams. I give an example. For example, if your streams MBW is 10.8 grams, then from the curve, we can find in the curve that is corresponding here, when the MBW is 10.8 grams, for 10,000 streams, the feeding amount 3.08 kg. So this is the output of our machine learning model. You multiply your stocking density, stocking numbers, and minus the mortality, you will roughly know today how many kg feed is required for the streams for the pound. So this is the curve is some like the output of the machine learning model. So every time you base down this curve to calculate, then your question is how we generate this curve. So you see the green dot here. The first we need to plot the green dot on the canvas. Then we use machine learning model to fit and find the curve to find the curve fit the trend of all the green dots. So there are two steps. First step is plot all the green points. Second step is using machine learning model to fit the plot with a curve. Okay, next slide.
For this, for this model, you just highlight the general model based on the data we have been collecting in Vietnam and Indonesia, or is there any other factors that also consider here, like maybe region, season, or stocking density, something like that?
Yes, so far the model we combine all the data we have, Vietnam, Indonesia, Singapore, all the data we have, because actually we don't have enough data types. But your idea is our future plan. We will, for example, Vietnam will have Vietnam the curves, Indonesia will have Indonesia the curves. I know Indonesia is very big, maybe different island will have different curves. And also you see maybe the feed type is from like group S or from CP. We can also plot this curve, but the first thing is we need to got data. So that's why we hope the farmer can use Aqua Easy app. We input the data, then we collect data, then we can optimize the feed.
Okay, I see.
Okay, on this slide, I will introduce how we plot the green point. So please remember in the last graph, we have green dots. This graph, we have a blue dot. You'll see the blue dot represent one farm data. So for example, this plot show like when the MBW is between 10 grams to 12 grams, we have in our history, in our database, we have 185 pounds data. Each pound, the farmer have already do some experiment. For example, the daily feeding for 10,000 streams is roughly from 2 kg to 5 kg. And they also do the MBW check. We can know the daily growth, the grams per day. So from this graph, it's a kind of statistic analytics. You can see some farmers try 2 kg for 10,000 streams. They can get the daily growth about 0.3, 0.5. Some farmers are unlucky. They even dispense 5 kg for 10,000 streams, but the daily growth is still the same. So all the farmers try their secret recipe, secret method functions. Then from here, we can see roughly most of the time, if you want to guarantee some 0.3 daily growth, the best feeding amount is about 3.34 kg for 10,000 streams. So this is a kind of mathematics and statistical analytics. We use the history data to analyze and tell you when the shrimp size is between 10 grams to 12 grams, the best feeding amount for them is roughly 3.34 kg for 10 shrimps. If you dispense more, you waste your money to buy the feed because the shrimps maybe don't have a high probability to grow bigger. If you feed less, sometimes the shrimps cannot grow as expected. So we use a lot of history data to find the highest probability of the shrimp's daily growth, and we then optimize the feeding amount. So all these blue points, we transfer from this histogram and the statistical analytics into some like Gaussian distribution, some mathematical function, and find a 1 point. So this 1 point is a 1 green point in the graph in the previous slide. Then each farm have some shrimps like from the 4 grams to 30 grams. So we can plot a lot of these kind of statistical analytics and the distributions. Then we can find the green point and put into the previous slide. So this is how we find the green point location and generate the feeding table. Okay, besides the machine learning model, I also want to explain why we need the MBW record. The machine learning model first input is the MBW measurement, but actually when we're feeding the shrimps, actually we are not using your measurement. We predict the next week daily growth based on the previous MBW measurements. So we have 2 plots here. The first one is you see from DOC roughly 10 to DOC 80, we have a lot of MBW measurements. So we use a machine learning model to predict in the next 10 days how the shrimps grows and what's the expected MBW measurement. So it's not based like I want to the daily growth is 0.3, 0.5 grams. No, we use a machine learning model to predict based on your history. So the next plot is that, for example, we only have 3 points, but the machine learning model still can do prediction for the next 10 days or roughly a week, 1 week, how the shrimps grows before your next MBW measurements. And we use this predicted MBW measurement, put into the machine learning model, the feeding amount, feeding table, the curves, then we get the feeding amount for the next few days. Roughly it's 1 week. I think in Vietnam and Indonesia, we always do the MBW measurement once per week. So the feeding table, you see the feeding table in Gateway will be updated once a week, every time after you measure the shrimps MBW. So this is how the feeding table generated. I want to emphasize important thing is we need to measure the MBW, and we also need to know the mortality and the stocking numbers. That is a very important input to guarantee we have a good feeding amount. Okay, now we will introduce the shrimp talk. So actually, shrimp talk is just transfer the hydrophone signal to convert it into some user-friendly and understandable message. So for any farmer, any technician, if you let them see the hydrophone signal, it's a little difficult, not easy to understand. So we will make it easy to be understand. We will transfer to this like a WhatsApp message. So we will tell the farmer each pound how the situation now is hungry or they need more feeding. And also you can see in roughly every 2 hours, how many feed has been dispensed into the pound and what's the response. So this is like more friendly user interface. We'll let the farmer use our feeding response, the hydrophone signal. And the last thing is stress analytics. So this one is we find when we do the iFeeder trial. So as I said before, if the shrimps are healthy, they behave calmly, the signal will stay at a low level, and there is no variance. This is the normal figure show. You can see after feeding, during the midnight, during the whole night, roughly the shrimps, the response is very calm. The processed signals stay at a very low level and stable. But sometimes we will discover the stressed signal. So you can see after the feeding, in the bottom figure, after the feeding, the shrimps come down for a moment, then suddenly we don't know what happened. The signal increase to a very high level and maintaining this level. And also you experience some high variance. So this is a kind of stress. And this stress may impact the daily growth or bring disease, but so far we don't know. And also we don't know what's the reason make the shrimps become stressed. So now what we can do is we can only tell the farmer, last night your shrimp is normal, it's calmed down, or your shrimp is stressed. So maybe the farmer, once the farmer know the shrimps is behave stressed in the last night, they may be more careful to check the shrimp in the pond, maybe use more frequently check the feeding tray or do other checks. Water mortality monitoring, for example, we can use LAMO to test the water quality to do this kind of prevention. So that's why we want to show this stress analytics to the farmers to help them to know more about the shrimps.
We see.
Yes.
Okay. When we inform to the farmers, the pond is have a stress level. We just inform like that. So all the treatment for the farmers is based on their pond, right? If any suggestion to the farmer from us how to do the reduce the stress level.
So far we can only tell them the shrimps is stressed, but how? I think we.
Okay, so from our system, right? As the best that we can do now is we can tell the farmer that your shrimp has fever, but whether the fever is caused by, example, I'm just saying for example, your shrimp has stress, they have fever, but we don't know whether that fever comes from flu, comes from infection, cut infection or something like that. These are things that we have not enough data to nail down to, but we know we can detect this fever. So when we detect the fever, we tell the farmer, yes, something is wrong, your shrimps are stressed, they have a fever. You understand what I mean?
Yeah, I understand. So just like a mention to the farmers, your shrimp is not healthy, have a stress out, but we didn't have a suggestion for the farmers, right?
Okay, so to find a solution, right, we need to go back to the shrimp consultation that Ruzia is talking about, when we bring all our aquaculturists together to look at the problem. Maybe they have disease, what are the symptoms, and then we can maybe narrow down on actual problem. We can look at nitrate levels, we can look at the ammonia levels, then maybe we can figure out something that we can recommend. But as of now, for the feeding portion, what the system will do is the system will just reduce feed, that's all. Yeah, but what to do to treat the water and all that, this is a lot more complex problem that we have not yet looked into. Does that answer your question, Sifa? Sorry. Yeah, I know I didn't answer your question, but basically that's the best we can do right now. When we know that there's stress, at least the farmer can look into that particular point to find out what's wrong and pay more attention. Out of maybe, I don't know, 20, 70 ponds or something like that. So far, this is the best we can do.
I think from my side, I think for that, maybe our app, we cannot recommend like what to do, what to treat for the farmer, but at least maybe from outside, our guy can support them to check like water qualities or check the feeding tray, shrimp behavior, whatever may cause the problem. And then maybe just inform the technician on the route to check, confirm again. So that the thing we can do. But like to ask like our apps to tell the farmer what to do, what to treat, maybe it's very difficult and also very risky for us also.
At this point, also we don't have all-inclusive data sets to help us to do this. It's something that we can work on in the future, but education for us at the moment. For example, we always recognize. We seem to always see a correlation between this stress level and nitrite levels. This is another interesting part about this. Yeah.
Just can you come back to the slide stress level?
Okay, this slide.
Okay,
Yes.
but can I answer your previous question first when you asked about how do we know this signal is from the streams or
Okay.
you-
Okay. Yeah.
it's always high,
Sure,
right?
Yeah,
The
sure.
answer is we don't know. We need to troubleshoot what is wrong. But if it's from the stream, what will happen is that from my experience is that if they go stressed, they go into high stress mode, especially when they are molting, you see these signs, high stress signals maintained for 2 to 3 days, but it will return back to normal. It will recover. And if it does recover, then typically these signals are from the stream. Yeah, but if you have a pond where it's always high stress, regardless of what you do, you also high stress, then typically something is wrong with the signal. There's some interference or something like that. But on a normal operation, you see the normal condition. Typically, they will return back to the normal condition after a couple of days. For example, if for example the farmer decides to stop feeding a few days, then you find that actually gradually the streams do return back to normal. Yeah, this recovery sign, this signal for the recovery sign is important for us to know whether the streams are the signal is actually from the streams or not.
Okay, so it means that we need to observe the like some patterns in a period of time to confirm.
Yes, and this period is important because we cannot just base on maybe 1-2 hour analysis to say that this is what's happening. For example, molting, depending on the percentage of molting that's happening in the water, it can persist from our experience, it can persist from as long as 4 to 5 days. Yep. But the interesting part about this is if we don't do anything, the streams will automatically start to recover across the days. And then you find that after the 3rd, 4th day, the stream goes back to normal behavior.
Okay. Okay, I see.
And these high stress periods, typically what the system does is, like what Chu Si explained to you, the system will start skipping feed so that actually less feed is dispensed into the water.
Yeah, that's also the question that I wanted to ask is because here I see that the stress level also last time you told me that the stress level is only detected like during nighttime when we don't have the feeding. So it means that when we have the feeding, we cannot detect the stress level, or it's more difficult to detect, or how does it work?
Yeah, actually, the stress I prefer to detect during the midnight. No feeding, no other human intervening. Then we know this is sound generated by streams. If you detect during the feeding, actually it's very difficult because sometimes the streams are very actively and the signal is not easy to detect. And to detect the stress, I prefer to use a long time, like 3 hours time. So we will do some calculation or analytics based on a long period. If you detect during the feeding time, the variance and the disturbance will be very frequently. So that's why I say we can only do this detect once per day and do it during the midnight.
Okay, so so it means that like maybe some customer they want to do the feeding like 24 hours, then we should have like some kind of recommendation like, okay, if you want to see the stress level of stream, you should not like do the 24-hour feeding, right?
Yeah. Actually, we don't recommend to 24 hours. Because we think the shrimp still need some time to rest or to do some other activities, not just.
Okay, we did some trials before for 24 hours feeding. We always never get good results because 24 hours feeding means that we need to always have some bit of feed in the water to see if they respond to the feed, and we always end up with excess feed. So we actually think that especially during the early mornings, we see the streams from our experience always never seem to feed well. So actually that what we do recommend is for the early period is for the shrimp to stop feeding, at least for that period that chooses identify 12 to 3 a.m. Typically, that period, I think we should stop feeding. We also need to stop feeding also because we need the water to recover. I think also that is the other problem, because if you keep throwing feed into the water chemistry is always going worse and worse, and there's no period of time that the water can actually start to recover. So this is also another. Actually, we don't recommend 24 hours feeding.
Okay. Yeah, it's interesting to share, because last time when we did the trial with OK guys also asked why don't we do the 24 hours, because they said their experience with the like AQ1 or their knowledge shrimp is and the nighttime feeder, so so they think that maybe feed it during nighttime shrimp may grow better. But
I know there's this trend of thought, but so far we haven't found any proof on this. In fact, we think otherwise. So we can have a long period of feeding, but we should have every day. We should have a period, and we recommend this period to be in the early morning to actually stop feeding, so that actually both the shrimp and the water can have a period to recover.
Okay. Also, I think it's more important also from the humans resource-wise also, that during nighttime if anything happen, then nobody's no, then it's a big trouble for us also. Yeah. Okay.
So the other thing that I want to input to is that these stress levels don't just appear actually in the early mornings. It will appear also during the daytime feeding. It does actually appear, especially in Singapore. The Singapore trials that we do here, we do see the stress levels in the daytime during feeding time also. Yeah. And typically the shrimps actually, typically for our system, we just reduce feed in those situations. And if the signal recover, then the system will go back feeding normally. Yeah. The other interesting part about this iFeeder system is that actually when there is heavy rain, these stress signals consistently show high scores, like what you see in the stress period. And the good part about this is when the system sees that, you also reduce feeding. So automatically during raining periods in open ponds, our system actually starts skipping and reducing feed.
Yeah. Okay. Interesting to see.
Okay. Any question from?
Do you meet you? Any question? Just ask.
Yeah.
To be side.
Yes, I have a question. As you know that the parameter that you can control the feeding activity, my question is which parameter or the water parameter can control the feeding activity, except the DO, exclude the DO.
Yeah, currently we only use DO because we find that this. So if we don't, okay, so when we have a sensor in the water, typically the DO, we are able to read the DO, and therefore we can put a threshold to the DO so that we can stop feeding when it drops below certain levels. If we don't use a sensor, actually the shrimps will also react and they'll start getting stressed and they'll maintain that high stress level. The problem is that now when we don't have a sensor, the system will reduce feed, but we won't know what the DO levels are at. So there's no way for us to track this except somebody going there to measure it. So far, this is the only parameter that we integrated. The other parameters, we have thought about it, but we haven't yet included it.
But how about the other toxic gas like NO3, NO2, nitrite, ammonia, something like that?
Yeah, so these are interesting values that we collect also, like the nitrite levels and the NH3 levels. The only problem is we need to figure out how to deal with these levels. For example, if the farmer measures the water parameter and they find NH3 to be at the high levels or nitrite to be at high level, the question is, do we just stop feeding for the next 2 days because the nitrite levels are high? Do we continue to feed but reduce it? By how much percentage of feed reduce? These are all questions in our minds that we have no clear answers to. And if we are only doing a reading once a day at best, then my question is that once a day reading, how do we translate that into proper feeding practice is also a problem, right? You know what I mean?
Yes, I understand.
So if we, for example, if we have a sensor like the in situ for the nitrogen cycle, right? Nitrate, nitrite, ammonia, total ammonia, and ammonia itself. Then, and we have regular readings of this every 10 minutes. Then maybe we can include this confidently and say, oh, we can control this using these parameters. Yeah, if it's just once a day reading, my question, yeah, then it'll be very hard for us to make decisions based on just that one reading of the day. You know what I mean? So that's why we're trying to come up with a proper solution based on this just one reading.
Okay, understood. Thank you. And I also have the other question is in the case the customer do not use the Awatron Farad or they did not measure the DO. So in that case, how can we control our feeder?
Okay, so this we have to ask the streams. The streams. Okay, so from our experience, we know that when DO is very low and all that, the streams will react, and our sensor will capture this signal. But this signal does not translate to any drastic actions like stop feeding. It only will end up reducing feed. So the humans still need to step in this case because we don't have magic, right? We cannot magically decide what the DO is because there's no sensor inside.
Okay.
So the reacting to and showing stress levels, or the signal will drop very low, and because the streams are hiding and starting to surface to the pond surface, and then the system will start dropping feed to 50%, right? Which is the minimal cap. Yeah. But then at this point, if the human does his job to monitor the pond and do regular readings, actually they should have already detected this. Yeah. While our system is trying to manage the situation on the ground by reducing feed, the farmer should have actually already taken some actions.
Okay, I got it. And I heard that we need the NVW information for updating on the feeding table when we operating the iFeeder. So how frequency of NVW should be updated? I mean every week or every 1 or 2 days is better?
I think every week is good enough because every 1 or 2 days is we may suffering the sampling issue. Sometimes the NVW may decrease if you measure every day. So if the farmer can do the NVW measurement regularly every week, it's good enough.
Okay, thank you.
Yes, and another thing, before they use iFeeder, when the streams is very small, we also hope the farmer provide the data, especially before for example, the stream is lower than 2 grams. We also hope the farmer can input the data into our website.
Okay, I got it.
I have a few questions. So can you go back to the slide of the machine learning models of the green dot and the blue dot? Yeah, the green one.
Yes.
Okay.
This one. Okay.
For the this machine learning is you said that we are able to predict the like, for example, like the MBWs in the next few days, something like that. So
it's not this slide.
Oh yeah.
I think this
this one.
Yes.
So this machine learning is mainly based on the like, for example, the current trend of the green dot that we have, also based on mainly based on the data in the past crop, something like that.
Yes, correct. So far, I have to say this model is not the perfect model, but it can give roughly an estimation and prediction of the MBW.
Okay, but I mean, is the prediction is mainly based on the current trend or based on the data set that we have in the past, or is a combination of what?
It's only based on the current trend. This pound, this pound and this pound BW.
Okay.
So this the MBW projections don't need to be super accurate. I mean, if it's super accurate, of course, it's great, but it doesn't need to be, because on the ground, when the streams responds with demand for feed, they will still be fed additional. So the system still copes with this on its own.
Okay. Another question is about the hydrophone. It's currently right now we put like 1 hydrophone. The first question is that correct to say that is like with the smaller ponds? I mean, the size of the pond, the size is smaller, and the higher stock intensity we will get the better signal from the stream. And the second question is, for example, if we have a bigger ponds, if we put like 2 hydrophone, will we get better signal, or we just still need like 1 hydrophone is enough? If so, it's more about an economic problem, like we put two hydrophone is more expensive, or
So we did trials here also. Chilsi have done some experiments with multiple hydrophones in the water, and definitely if we have multiple hydrophones, we can get a better picture of what's happening in the ponds when we start to look at the different signals from different parts of the pond. The problem is we're going to go bankrupt before we deploy the solution to the ground, because the price is going to be expensive, and we have a limitation also. We cannot deploy so many hydrophones. So the best way we have figured out to do this actually is we control the feeding area. That's why hand feeding actually is discouraged, because in hand feeding we cannot control the feeding area. But if you use a auto feeder, then the throw area of the auto feeder actually results in us being able to control that feeding area. And when we can control that feeding area, the streams will go there to feed, and we will have our hydrophone there picking up the signals. We have give us a higher chance of getting the right signals from the streams. So to answer your question, more hydrophone will definitely help, but it will not be economical for us. In fact, we have been given the ultimatum to reduce the cost rather than increase the cost. So we also have our limitations, and the best.
Because this is actually a question from the Wake Up guys. They were asking like, just like they have like 500 square meter ponds, or maybe some pond is bigger, and we just put like one hydrophone. Is that hydrophone is representative enough to get the stream signals? Because stream is everywhere, not just in that hydrophone areas actually.
Yeah, so in this case, right, what we recommend is just use 2 auto feeders, separated apart, and then we have our hydrophone position in one of the auto feeder location.
Okay, maybe okay to answer the question for them is because with one hydrophone we are trying to get like the best position where we get like the feed is the concentrated there, also the stream is there, so right.
Yeah, because this signal is important, right?
Yeah.
To deal with the bigger ponds, what we can recommend is to add additional auto feeder, but still keep that.
Hello.
Yeah.
Okay, any more question?
Hello, I have one question about hydrophone. Yeah, I found a lot of hydrophone in the market. What is the spec of the hydrophone that we need? The frequency or the resonant frequency, anything? Because if a lot of hydrophone need a cheaper, have a cheaper price.
Yes, we have a lot of hydrophone at a cheaper price. The problem is also maintenance, right? If we have to always pull out the hydrophone and clean it and retune it, then we have a headache. This hydrophone actually works very good because it's ceramic, and that we found that actually when we deploy this in the pond for 140 days, we don't need to actually pull it out to clean it at all, and still we can get good signals, normal signals from it. Yeah, so we need to be careful to balance also this, because if the farmer needs to pull out the hydrophone and clean it every 3 days and retune it again, this will be very problematic for us. Yeah, not only for us but also for the farmer.
Okay. For the deployment of IPDAS, the gateway configuration can be done by the CS team, right? Not just some IT guys or the team in Singapore, right?
Yes, actually, for example, the one that Stephen showed you, if the farmer decided for whatever reason today he don't feel good, he want to stop feeding, then your site can just go to the app and find that particular pond and stop the feeding, and the feeding will stop.
With the gateway configuration, you can find some way to. Sometimes the panel cannot connect to the internet. You can find some way to. We can use a phone to connect to the same network with the router and config with the app or something, because sometimes you cannot connect the panel to the internet properly.
Yeah, so this is a known problem. What the system that we have today in the gateway is, it will actually try to buffer the data and the instructions, and once it gets connectivity, it will actually push these instructions or the data back onto the cloud. Other than that,
I think his question is, if you want to stop it now, but no internet now, how do we stop it?
Okay, if you want to stop it now without any internet, actually you need to open up the panel and flip a switch, which you have to ask Luming. Yeah, Anything go wrong, Lu Ming will in the chopping board.
Ask Katrin to show you.
Now we can take this offline if you want to make some switch, like just. I mean, for now we have the switch to just off the feeder.
He occurred this problem one time in Vigo. Yeah, he turned up already on app, but it still works.
Because no internet.
Okay.
That's what happened.
So actually, maybe Lu Ming can share with you all how to actually physically disconnect the.
I mean, Nam, you should know, right? It's just that, I mean, if not for us, some normal people, I mean, the CS team, any other guy, okay, they need to know which switch to turn off.
Okay, I will share with the CS team with them.
Yeah, you have to share with them because you know.
Okay, any more question?
I think we missed one very important information. This eye feeder, we should apply this eye feeder only when the stream is bigger than 2 grams. So everyone should.
So our previous trials, we also figure out that actually when the streams are too small, and let's say if the stocking is not very high, we are unable to detect the reaction of the streams because the reaction of the stream is not strong enough to basically pass the baseline. I mean, make a change in the baseline. So what we recommend today is that the stream should be bigger than 2 grams before we start the eye feeder. And typically, when they are very small like this, is blind feeding. Most farms, I think, actually all the farm I know still practice blind feeding. And blind feeding, they use powdered feed and maybe crumbles. So the auto feeder also cannot be used in that case. Yeah. So for these reasons, we only recommend the eye feeder after it passes 2 grams for intensive ponds, not for extensive ponds. The other also, we also found out that other researchers in Australia also recommend the same thing after 2 grams. So I think the findings are consistent.
Okay, any more question? If no more question, I will proceed.
Okay, this is a job given to us by TC. Okay, he wants you all to vote 1, 2, 3, 4.
Yeah. Then how do I do it?
So can you all type in the chat which one you prefer, and then we'll collate the results and give it to.
Yeah.
So
No, we don't use Stream Talk.
We are trying to register the trademark for Stream Talk, but it turns out that Uruvaka actually already trademarked Stream Talk, so that we cannot use that term anymore. And that's why we are actually looking for an alternative, and we are asking your opinion on which one you think should be better. Which one is better? Which one do you like to use?
Number 3.
So okay, you know the chat function in Teams, right? Can you just put your number there, and then later we'll collate it from there.
Okay, let's vote.
Vote.
I also number 3.
In the future, we go Morazan and Mono Talk.
Oh, whoa, where's the chat?
About stream speak, stream shout,
Stream screaming.
stream cry, stream laugh.
Okay, yeah, voted. Thank you for your time.
Yeah.
Thank you for listening to us. If you have any question, please come back to the team. You know all the different people that were in the training. We've introduced the different people in charge of the different areas in the product. Please feel free to drop us an email or talk to us.
Yeah. Thank you, everyone. Thank you, everyone. To Stephen, Luming, and Rosia also for organizing it for the team. I think from our side, especially Vietnam's team, we will have some internal training again in Vietnamese, and we can have a sharing on after this training. So make sure everyone understand the same things. If we don't have anything if we have anything like not clear or conflict between the member, we can come back to you to ask again.
Yes.
Yeah, no problem to us. Just send us the email about questions.
Yeah. Sure.
Yeah.
Okay, guys.
Once you have voted, you can drop out. Thank you.
Thank you, everyone.
Stream complaint.
Mọi người vote nha, mọi người vô cái hộp chat bóc vote số cái số nào mà mọi người thích nha, tại bên Sinh họ đang yêu cầu vote à.
Cho em thêm số 3 đi anh ơi, em không có
Chịu hả?
1, 2, 3, 4 nào thích chọn vô.
Cho em số 3 anh ơi, em không có chat box anh ơi.
Dạ, ok, Nam số 3. Nhập không được nữa không? Nhập luôn cho.
Em số 3 luôn nha anh.
Sang số 3. Rồi mọi người sao? Còn người khác còn quên rồi. Hào, Cường, My.
Em gọi.
Rosia.
Em gọi.
Panama Talk.
Ủa sao có Việt Nam mình vote không, Indo không ai vote chẳng vậy?
Where's Indo voting? Hello.
No Indonesian college voting. Sifa, are you still thinking, Sifa?
Yeah.
Still thinking which number?
Yeah.
Difficult to select.
Correct, because I think it's very new. Yeah, information is for the marketing team is didn't show what is the voting for this.
TC doing all things, even marketing.
Okay, this training is still continue.
No, I think it's finished already.
Okay, maybe everyone can leave. Yeah.
Okay.
Thank you everyone for the time.
Okay, thank you everyone.
Bye.
Thank you everyone.